Hey everyone, welcome to section 8.3, all about simplifying rational exponents. The goal of our section this time around is to write radical expressions in terms of exponents, so that we're all kind of using the same thing. We're not using radical symbols as much. So let's say I wanted to write the fifth root of 3 as an exponent. But I don't know what that exponent should be. Let's remember that this rule of exponents says when we raise powers to powers, we multiply the exponents together. So I know that when I would take the fifth root of 3 and raise it to the fifth power, I should just end up with 3 on the left-hand side. On the right-hand side, I would have 5 times whatever my exponent is. But the exponent of 3 here is 1. And so we have that 1 is equal to 5 times whatever. So it's not too hard to see that that mystery exponent has to be 1 over 5. And that's how we're going to be writing radicals in terms of exponents. That is, we are going to take the nth root of a, and we are going to say that that is equal to a to the 1 over n power. So first up on our batch of examples, we want to write each of these guys as a radical expression. We're going to get used to translating back and forth. So x to the 1/5 power is the fifth root of x. Y to the 1/3 power is the third root of y. And r to the 1/4 power is the fourth root of r. That's not so bad. We want to go the other direction. The index of a square root is 2. So 5y under the square root is equal to the 5y raised to the 1/2 power. Similarly, for the second guy, we would have 4x raised to the 1/3 power. And for this third expression, I have 3 times 5z raised to the 1/4 power. And we want to be careful, we're not raising this 3 to the 1/4 power because it's outside of the radical. All right, now let's look at a different fractional exponent. I want to know what 4 to the 3 over 2 is going to be. And, you know, if we think about it, this is 4 to the 3 times 1/2. So thinking about rules of exponents again, I would have 4 cubed all raised to the 1/2 power. So this would be the square root of 4 cubed. Or, we know that that multiplication is commutative, right? So this could also be rewritten as 4 to the 1/2 times 3, or 4 to the 1/2 cubed, which would be the cube of the square root of 4. Since the square root of 4 is 2, this would be equal to 8. So with that principle in mind, we are defining a to the m over n power as equal to either the nth root of a raised to the m power, or the nth root of a raised to the m power. Either is okay. So if we want to rewrite each of these guys, we can rewrite the first as, since we're taking the square root of x to the 5th, this would be x to the 5 over 2. We're raising a 4th root to the 3rd power. So this would be 3y to the 3 over 4. Next one, I'm raising a 3rd root to the 5th power. So this would be 5ab to the 5/3 power. And finally, I'm taking the square root of 7xy over z all cubed. This would be 7xy over z to the 3/2 power. All right, remember our discussion about negative exponents and what that means. So negative exponents means I take the reciprocal of that number. So this is equal to 1/16 to the 3/2 power. And that's equal to the square root of 16 cubed, which is 1/4 cubed, or 1/64. So when simplifying rational exponents, we have to keep all of our properties in mind, and we want to do things the correct way. As a refresher, these are all the properties of exponents that we know. The product property, the power property, product to a power, quotient property, zero exponent, quotient to a power, negative exponent properties. All right, so we want to start combining different properties of exponents with rationals. For the first expression, when we multiply like bases, we add exponents. So this would be x to the 1/6 plus 4/3. And we know that we need a common denominator. Now, I would highly suggest doing some side work to figure out what 1/6 plus 4/3 is. We need a common denominator, of course. So this is equal to x to the 3/2. For the second expression, I have m to the 9th raised to the 2/9 power. Well, that means I multiply the exponents because I have a power raised to power. And on our quick aside, 9 times 2/9 is 2. So this is m squared. And now looking at the third expression, I'm going to be subtracting. So this is equal to d to the 1/5 minus 6/5 equal to d to the -1. If it makes you feel better, you can write that as 1/d. All right, another one. Remember that when I have two factors under the same exponent, I can kind of break it up. So this would be m to the 2/3 raised to the 3/2 times n to the 1/2 times raised to the 3/2 power. Okay, first factor, I would be multiplying together the exponents, but I know that 2/3 and 3/2 are reciprocal, so this is really just m to the first power. And I have n to the 1/2 power raised to the 3/2 power. When I multiply those exponents, I get n to the 3/4. 1/2 times 3/2 is 3/4. All right, so here's the true test. See if we really are getting it. We want to simplify this abomination. So try it out. I have no way of knowing what you're doing, so I'm going to start writing. What I'm going to do is do my subtraction of exponents. I'll have 25, and then I'll have m to the 1/6 minus 2/3. Then I'll have n to the 11/6 minus -1/6. Yeah, I know. And all that's raised to the 1/2 power. A little bit of side work. I'm looking at 1/6 minus 2/3. I need a common denominator, which is 6. So 1/6 minus 4/6, -3/6, or -1/2. Okay. And 11 over 6 minus negative 1 over 6 is positive 12 over 6, which is equal to 2. So this simplifies a bit to 25m to the negative 1/2 power times n squared raised to the 1/2 power. And now we're going to break up these factors with that 1/2 exponent. All right, so a half exponent is really just a fancy way of saying square root. Square root of 25 is 5. I'm multiplying my exponents, so I would get m to the negative 1 over 4. And I have n squared, and I'm taking it to the 1/2 power. In other words, I'm taking the square root. So that would be equal to n, but don't forget your absolute values around the n. N being a variable, we're taking an even root of it. All right, you made it. So we're going to be skipping doing operations with radical expressions. It's just, it's really cumbersome, and you can make a lot of mistakes really easily. So I don't think it's a good use of our remaining time. Instead, what we're going to do is skip ahead to solving radical equations, which we can do some of.